In the last lecture, we have discussed about virtual memory, implementation of virtual memory using demand paging and various page replacement algorithms. In this lecture, we will discuss about various aspects of file management including basic file operations and their implementation, directory structure and directory implementation. We will start with file management. File management is one of the basic functions of operating system. Permanent information is stored in computers on several different types of secondary storage devices like magnetic tape, magnetic disk, optical disk, etc. File manager is responsible for the maintenance of secondary storage. Some of the primary functions of file management includes: first, file management ensures to meet the data management needs and requirements of the user, which include storage of data and ability to perform the basic operation as creation and deletion of files, creation and deletion of directories, mapping of files on secondary storage devices, backup and recovery of files, accessing of files and directories using different strategies, etc. File management ensures the consistency of data when multiple users access files concurrently. File management also provides the measures for file security and protection. Fourth, it optimizes performance both from the system point of view in terms of overall throughput and from the user's point of view of response time. Fifth point, it provides input output support for various storage devices. For doing this, the operating system abstracts from the physical properties of storage devices to define a logical storage unit called a file. User is not worried about the hardware storage of its data, as operating system abstracts user from hardware details of providing standardized set of input output interface routines. First of all, we are going to discuss files. In a computer system, data is organized in files. Major properties of files are: a file is named collection of logically related data permanently stored in a computer system. The operating system abstracts from the physical properties of its storage devices to define a logical storage unit called a file. A file consists of related information that is stored as a sequence of bytes and records as defined by its creator. Commonly, files represent programs and data. Files are further organized into directories and subdirectories. Data files may be numeric, alphabetic, alphanumeric or binary. A file has certain structure according to its type. There are many types of files like text file, source file, executable file, object file, etc. As shown in figure, your computer may have many types of files like doc, exe, PDF files, C, CPP, Java, PPT, TIFF, JPEG, etc. There are many attributes associated with each file like name of the file, type, location, size, protection, time, date, etc. Basic file operations. A file is an abstract data type. There are various operations that can be performed on files to manipulate or use the file. Operating system provides system calls to create, write, read, reposition, delete and truncate files. To perform each of these file operations, operating system performs a series of operations as discussed. First operation is creating a file. To create a new file of any type, associated application program calls the file system. The file system searches for space and if available, it allocates space to the file. After that, an entry for the new file is made in appropriate directory where file was created. Directory entry contains the name of the file and location of file in file system. Second operation is writing a file. To write something in a file, a system call is generated specifying both the name of the file and the information to be written to file. System searches the file in file system to find the location of file in appropriate directory. The system activates a write pointer initially pointing to start of the file to write the information in the file. Write pointer is automatically updated whenever a write occurs. Third operation is reading a file. This operation reads the information from a file. A system call is generated specifying the name of the file and length of memory block from where information is to be read from. The directory is searched for the required file name and system maintains a read pointer to the location in the file from where the read operation is to take place. Once the read has taken place, the read pointer is updated. Fourth operation is repositioning within a file. This is an operation in which the file pointer is repositioned from the current position to a specific position in file. A system call is generated specifying the name of the file and specific position where pointer is to be repositioned. The directory is searched for the appropriate entry and the current file position pointer is repositioned to the specific position. Fifth operation is deleting a file. To delete a file, a system call is generated specifying the name of the file to be deleted. Directory is searched for the required file. Having found the associated directory entry, we release all the file space and erase the directory entry to delete the file. Sixth operation is truncating a file. The user may want to erase the contents of a file, but keep its attributes. The system call to do this resets the length of the file to 0 and file space is released. These primitive operations can then be combined to perform other file operations, that means copying, appending, renaming and many more. The operating system keeps a small table called the open file table containing information about all open files. When a file operation is requested, the file is specified via an index into this table, so no searching is required. When the file is no longer being actively used, it is closed by the process and the operating system removes its entry from the open file table. Most systems require that the programmer open a file explicitly with the open function system call before that file can be used. The implementation of open function and close function operations is more complicated in an environment where several processes may open the file at the same time. Next, we are going to discuss directory structure. Normally, every computer system contains a large number of files. Proper organization of these files is necessary. To keep track of files, file system normally have directories or folders. Usually, a directory is itself a file. The directory can be viewed as a symbol table that translates file names into their directory entries. A typical directory entry contains information about a file. Directory itself can be organized in many ways. When considering a particular directory structure, we need to keep in mind the operations that are to be performed on a directory like search for a file, create a file, delete a file, list a directory, rename a file, traverse the file system, etc. We may wish to access every directory and every file within a directory structure. The most common schemes for defining the logical structure of a directory are discussed below. First is single level directory structure. The simplest directory structure is the single level directory. All files are contained in the same directory, which is easy to support and understand as shown in figure. A single level directory has few problems when the number of files increases or when the system has more than one user. Since all files are in the same directory, they must have unique names. If two users name their data file temp, then the unique name rule is violated. Even a single user on a single level directory may find it difficult to remember the names of all the files as the number of files increases. Second is two level directory structure. The standard solution of problems with single level directory is to create a separate directory for each user. In the two level directory structure, each user has its own user file directory called UFD. The UFDs have similar structures, but each lists only the files of a single user. When a user job starts or a user logs in, the system's master file directory called MFD is searched. The MFD is indexed by username or user ID, and each entry points to the UFD for that user as shown in figure. When a user refers to a particular file, only his own UFD is searched to perform different file operations like create a file, delete a file, etc. Although the two level directory structure solves the name collision problem, it still has disadvantages. This structure effectively isolates one user from another. Isolation is good when the users are working independently, but is a problem when the users want to cooperate and they require sharing of files of each other. A two level directory can be thought of as a tree of height 2. The root of the tree is the MFD. Its direct descendants are the UFDs. The descendants of UFDs are the files themselves. The files are the leaves of the tree. Using this directory structure, subdirectories cannot be created. Next, we have tree structured directories. The generalization of two level directory structure is tree structured directories. This structure of directories allows users to create their own subdirectories and to organize their files accordingly. A tree is the most common directory structure. The tree has a root directory and every file in the system has a unique path name as shown in figure. A directory is simply another file, but it is treated in a special way. One directory or subdirectory may have two types of entries, files and subdirectories. One bit in each directory entry defines the entry as a file if 0, as a subdirectory if 1. Path names can be of two types, absolute and relative. With a tree structured directory system, users can be allowed to access, in addition to their files, the files of other users. Next, we have acyclic graph directories. In tree data structure, every file except the root has exactly one parent directory. The acyclic graph is a natural generalization of the tree structured directory scheme as shown in figure. The common subdirectory can be shared using acyclic graph directory structure. A tree structure prohibits the sharing of files or directories. An acyclic graph allows directories to share subdirectories and files as shown in figure. The same file or subdirectory may be in two different directories. In acyclic graph structure of directories, one file or directory may have multiple parent directories. It is important to note that a shared file is not the same as two copies of the file. With two copies, each programmer can view the file rather than the original. But if one programmer changes the file, the changes will not appear in others' copy. With a shared file, only one actual file exists, so any changes made by one person are immediately visible to the other. There are many problems using acyclic graph directory structure. A file may now have multiple absolute path names. Another problem involves deletion. When can the space allocated to a shared file be deallocated and reused? One possibility is to remove the file whenever anyone deletes it, but this action may leave dangling pointers. Dangling pointers are the pointers by other processes accessing this deleted file to the now non-existent file. This problem is enhanced if the remaining file pointers contain actual disk addresses and the space is subsequently reused for other files. These dangling pointers may point into the middle of other files. In a system where sharing is implemented by symbolic links, this situation is somewhat easier to handle. The deletion of a link need not affect the original file, only the link is removed. If the file entry itself is deleted, the space for the file is deallocated, leaving the links dangling. Another approach of file deletion is to preserve the file until all references to it are deleted. To implement this approach, we must have some mechanism for determining that the last reference to the file has been deleted. The trouble with this approach is the variable and potentially large size of the file reference list. However, we really do not need to keep the entire list. Instead, we need to keep only a count of the number of references. Adding a new link or directory entry increments the reference count, deleting a link or entry decrements the count. When the count is 0, the file can be deleted. There are no remaining references to it. Next, we have journal graph directories. Journal graph directory structure is an extension of acyclic graph directory structure containing additional links from files or directories of higher level to directories of lower level as shown in figure. This causes cycles in the directory structure. The journal graph structure solves the problem of a file having multiple absolute path names. If cycles are allowed in the graphs, then several problems can arise. Search algorithms can go into infinite loops. One solution is to not follow links in search algorithms. Other problem is that subtrees can become disconnected from the rest of the tree and still not have their reference counts reduced to 0. Periodic garbage collection is required to detect and resolve this problem. Also, allow upward links only to files and not to subdirectories. Next topic is directory implementation. Directories need to be fast to search, insert and delete with a minimum of wastage disk space. There are two methods to implement directories. First is linear list. A linear list is the simplest method to implement directory. In this method, a linear list of file names with pointers to the data blocks is established. This method consumes a lot of time while executing. To create a file, searching full linear list is required to verify that the same file does not exist in same directory already. Deletions can be done by moving all entries, flagging an entry as deleted, or by moving the last entry into the newly vacant position. Sorting the list makes searches faster at the expense of more complex insertions and deletions. A linked list makes insertions and deletions into a sorted list easier with overhead for the links. More complex data structures such as B trees could also be considered. All these operations require linear searching the list, which is a very time consuming process. Second method is hash table. Using hash table structure to implement directory, the elements are stored in a linear list along with maintaining a hash table. For every file to be searched, a number is computed on the basis of file name, and hash table directly returns a pointer to the file name in list. Hash table makes searching, deletion and insertion very fast and straightforward. However, collisions are to be resolved during this. Finally, we have conclusions. File management is one of the important functions of operating system. File management includes the proper management of user files on secondary storage devices in an efficient and effective manner. User is abstracted from the actual hardware implementation of file management. Operating system initiates many system calls to perform various file operations. For proper management of files on computers, directories are always required. There are many structures of directories having their own advantages and disadvantages. Linear list and hash tables are two methods for implementing directories. Thank you.